Hi everyone, today we're going to study exponential functions. Let us first define exponential function. The equation f of x equals b raised to x defines an exponential function for each different constant b called the base. There is a restriction that the base must be greater than 0. It means b must be positive. Also, b should not be equal to 1. The independent variable x can assume any real value. It means to say, for an exponential function, we expect a variable, which is x, as an exponent. Example 1, f of x equals 2 raised to x. In here, the base is 2 and the exponent is x. Here is a quick look of how the graph of f of x equals 2 raised to x looks like. Another example is f of x equals 1 over 2 raised to x. In this example, the base is 1/2 and again, the exponent is x. Here is a quick look on how the graph looks like. There is a note that the domain of the function is the set of all real numbers r, and this is the interval notation, negative infinity to positive infinity, and the range of f is the set of all positive real numbers, and this is the interval notation from 0 to infinity. Take note, we are using the parentheses for the 0, and 0 is not part of the solution. Let's go now to the graphs of exponential functions. Here are the respective graphs of our example a while ago. The y equals 2 raised to x and the y equals 1/2 raised to x. Let us study the properties of the graphs of exponential functions, and this is the first one. All graphs pass through the point 0, 1. This is the point 0, 1. Number 2 property, all graphs are continuous with no holes or jumps. Property number 3, the x-axis is a horizontal asymptote. Asymptote is a line that the graph is approaching but never intersect. If you notice the graph, it is approaching the x-axis, but it will never intersect the x-axis. Property number 4. If b is greater than 1, then the function b raised to x increases as x increases. This is an example of a graph with b, or the base, is greater than 1. Property number 5. If b is between 0 and 1, then the function b raised to x decreases as x increases. This is an example of a graph for property number 5. Number 6 property, the function f is 1 to 1. Let's go now to properties of exponential functions. Let a and b be positives, where a is not equal to 1 and b also not equal to 1, and x and y are real numbers. The first property is about exponent laws. Here are 6 examples of our exponent laws. Property number 1, when we have a raised to x times a raised to y equals a raised to the sum of x and y. Exponent law number 2, a raised to x over a raised to y equals a raised to the difference x minus y. Law number 3, ab raised to x is equal to a raised to x times b raised to x. Law number 4, when we have a quotient and this is raised to x, this is equal to a raised to x over b raised to x. Law number 5, a raised to x and the quantity is raised to y. This is equal to a raised to the product of xy. Law number 6, a raised to 0 equals 1. Property number 2 is a raised to x equals a raised to y if and only if x equals y. There is a restriction that a is not equal to 1. Property number 3, a raised to x equals b raised to x if and only if a equals b. There is a restriction that x is not equal to 0. There is a definition for exponential function with base e. For a real number x, the equation f of x equals e raised to x defines the exponential function with base e. This function will be used thoroughly in higher mathematics, especially in calculus. Take note that the value of e is the number 2.71828. And this is a quick look of how the graph of y equals e raised to x looks like. Let's go now to sample problems. Example 1. Simplify using laws of exponents and write answers using positive exponents only. We have 2 problems here, A, B. Letter A is 2 raised to 5x minus 1 times 2 raised to 3 minus 2x. So we have here multiplication of exponents with same base. So what we'll do is simply add the exponents. So we have 2 raised to 5x minus 1 plus the other exponent is 3 minus 2x. So we can directly remove the grouping symbol and add corresponding terms. So the 5x and the negative 2x we will combine together. It will be 3x. The negative 1 plus 3 is positive 2. So our final answer is 2 raised to 3x plus 2. For letter B, we have division of exponents with the same base, which is e. So we will subtract the exponents. So we have e raised to 4 minus 3x, then minus the exponent of the denominator 2 minus 5x. In the next step, we will remove the grouping symbol. In the first group, we can directly remove the grouping symbol, but for the second group, we need to change first the sign of the terms inside this grouping symbol. So we have now e raised to 4 minus 3x minus 2 plus 5x. And from here, we can combine similar terms. The 4 and the negative 2, we can combine together. It becomes 2. And the negative 3x plus 5x is positive 2x. So our final answer is e raised to 2 plus 2x. Let's go to example 2. Solve for x. We have two problems here, A, B. Let's begin with A. 4 raised to 5x plus 1 equals 16 raised to 2x minus 1. First, let us check if the bases can be made equal. We can see here in the left side the base is 4, on the right side the base is 16. And we know that this 16 can be rewritten as 4 squared. So it will be like this now. The 16 becomes 4 squared. And the power 2 here, we can multiply with our exponent outside. So the 2 times 2x becomes 4x. 2 times negative 1 becomes negative 2. On this line, we can see that the bases are now equal. And according to property number 2, a raised to x equals a raised to y if and only if x equals y. It means to say we can copy the exponents 5x plus 1 in here and equate that with the exponent of the right side, 4x minus 2. And from here, we will solve for x. The 4x on the right side, we will transpose on the left. Of course, the sign must be changed. Also, this plus 1, we will transpose on the right side. The sign will be changed. So, we have now 5x minus 4x equals the negative 2 and minus 1. To simplify further, the 5x minus 4x becomes x, and this is equal to negative 2 minus 1 is negative 3. Let's go to problem B. The quantity 2x minus 1 is raised to 5 equals negative 32. I know that this negative 32 can be written as negative 2 raised to power 5. And if I do this, I can observe that the exponent here, which is 5, and the exponent here, which is now 5, are now equal. So according to property number 3, a raised to x equals b raised to x if and only if a equals b. It means to say we can now copy the bases of the left side and the right side respectively. Thus, 2x minus 1 is now copied here is equal to the negative 2. And from here, we're going to solve for x. The negative 1, we will transpose on the right side. It becomes plus 1. And then we will simplify further. The negative 2 plus 1 is negative 1. We will divide this equation by the coefficient of x, which is 2. So we have now 2x over 2 equals negative 1 over 2. And we will cancel the coefficient of x and the divisor 2. So only x comes down, and this is equal to negative 1 over 2. This is our final answer. Hi everyone. Today we're going to study logarithmic functions. Let us define logarithmic function. For b greater than 1, the b is the base, and b is not equal to 0, the inverse of f of x equals b raised to x. This function is an exponential function denoted by f inverse of x equals log of x base b is the logarithmic function with base b. The general form of logarithmic function is f of x equals log of x to base b. So in here, the inverse of the exponential function is the logarithmic function and vice versa. We read this notation as log of x to base b. Please note that x equals b raised to y is equivalent to y equals log of x to base b. This is the exponential form, and this is the logarithmic form. As an example, if we have 3 squared equals 9, this is equivalent to log of 9 to base 3 equals 2. Take note, the number 3 here is the base of the exponent, and in the logarithm, the number 3 is also the base. The number 2 is the exponent, and that is the logarithm value of the logarithmic form. And this number 9 is the same number for the logarithm. Here is a quick look of the graphs of logarithmic function. This is the graph of y equals log of x to base b, where b is between 0 and 1. While this is the graph of y equals log of x to base b, when b is greater than 1. Let us proceed with properties of logarithmic functions. If b, capital M, capital N are positive real numbers and b is not equal to 0, and p and x are real numbers, then we have here the first 4 properties of logarithmic functions. Number 1, log of 1 to base b equals 0. Property number 2, log of b to base b equals 1. Number 3, log of this b raised to x to base b equals x. And this x is simply that exponent of the b. Property number 4, when we have a number b raised to log of x to the base b, this is equal to x, and this x is the number of the log. There is a condition that x is greater than 0. It means x must be positive. Let's have the 5th, 6th, 7th, and 8th properties of the logarithmic functions. Let's have number 5. The log of m to base b equals the log of n to base b if and only if capital M is equal to n. This property is used normally when we are solving equations. Property number 6. This is the log of a product mn. If we're going to take the log of the product mn to base b, this is equal to the log of m to base b plus the log of n to base b. Property number 7. This is the log of a quotient. When we have m over n, and we will take the log of that to base b, this is equal to the log of capital M to base b minus the log of n to base b. Property number 8. The log of this m raised to an exponent p to base b, this is equal to the p, which is the exponent, is now put down as a factor. So this is p times the log of m to base b. Take note of this property 6, 7, 8. Because the logarithm lightens up the respective operations. Look at the product. This is equal to the sum of each factor. For number 7, the division becomes subtraction. And for number 8, the exponent or the power becomes product in here. There are types of logarithmic functions and relationships. The first is the general logarithm, where we see y equals log of x to base b. The condition is b must be greater than 0, or we say b is positive, and b is not equal to 1. Also, x must be greater than 1. The next type is common logarithm, and this is equal to y equals log of x to base 10. We say that this is common logarithm when we have a base of 10. And if we have a base of 10, we can simplify the log notation into log x. So in here, the base is not written. So every time we see a log without any base, that is understood to be base 10. And we call this common logarithm. The next type is natural logarithm, and this is y equals log of x to base e. And we can simplify the notation by writing ln of x. This ln of x means it is a logarithm with base e. There is a relationship about log of x to base b. We can simplify this by taking the quotient of log of x to base 10 over log of b to base 10, or we can write ln of x over ln of b. Take note, the log of the x will be in the numerator, and the base, which is the b, will come as the log of b in the denominator. Let's go now to examples. This is example 1. Change each logarithmic form to an equivalent exponential form. We have here our conversion formula. So letter A is log of 5 to base 25 equals 1/2, and letter B, log of 1000 to base 10 equals 3. So let's start with letter A. This is the equivalent exponential form. Take note, this is log of 5, so we will write here the number 5 equals, the base is 25, so we will use this base as the base of the exponent. And this 1/2 here is exactly the exponent. So we have 5 equals 25 raised to 1/2. So this is the answer for letter A. For letter B, the equivalent exponential form is 1000 equals 10 raised to 3. From the given problem, log of 1000, we're going to write this 1000 again here, and this is equal to the base 10 of the log is the same base for the exponent, and this number 3 is the exponent in here. So 1000 equals 10 raised to 3. This is our final answer. Let us have the reverse process. Change each exponential form to an equivalent logarithmic form. Again, let us write our conversion formula. And we have two problems here, A and B. This is 36 equals 6 squared. And letter B, 7 equals square root of 49. Let's begin with letter A. And this is equivalent to 2 equals log of 36 to base 6. Now, this number 2 is the exponent of our exponential form. And we write equals. We put the log of the number 36, we copy here. And the base 6 of the exponent is the same base of the logarithm. So this is our answer for letter A. Now for letter B, 7 equals the square root of 49. Let us convert the square root of 49 into rational exponent. So we have 7 equals 49 raised to 1/2. And from here, we will now write the equivalent logarithmic form. This is the equivalent logarithmic form. The 1/2 or the exponent in here will be our answer here, 1/2, then equals. We will write the log of the number 7, we will write here, and this base 49 of the exponent is the same base for the logarithm. So our final answer is 1/2 equals log of 7 to base 49. This is our final answer. Let's have example 3. Find x, b, and y as indicated. So we have here 3 problems, A, B, C. Letter A is log of 16 to base b equals 2. Letter B, log of 64 to base 8 equals y. Letter C, log of x to base 2 equals 3. First, let us write our conversion formula here. Our main goal now is to convert each of these problems into equivalent exponential form and solve using exponential property. Let's begin with letter A. The equivalent exponential form of letter A is b squared equals 16. The b is the base, so I write the base here, and this number 2 is the exponent, so we have b squared. And this is equal to this number 16. Now, I know that this 16 is the square of 4. So I can show that b squared equals 4 squared. And then I'm going to use a property of exponential function. I remember there is property number 3 that says a raised to x equals b raised to x if and only if a equals b. I can see here that the exponents are the same. So it means I can simply copy the b down here equals 4. So I have here b equals 4, and this is my answer for letter B. It means the value of b equals 4. I will just copy this answer opposite letter A. I will go now to letter B. I will convert this into equivalent exponential form. And this is the exponential form. 8 raised to y equals 64. Again, we see the base here, the log with base 8. I copy that same base in here. And this y is the exponent that I can use here. So 8 raised to y. And this is equal to, this number 64 is now here. And I know this 64 is equal to 8 squared. So I have now 8 raised to y equals 8 squared. In this portion, I can see that I have same base for the left and the right sides of the equation respectively. So I remember property number 2 of exponential function, and that is a raised to x equals a raised to y if and only if x equals y. I can see that I have same base, so it means I can copy the exponents of the left side, which is y, and this is equal to the exponent of the right side, which is 2. So I have now this equation, y equals 2. And this is the value of y that I want to derive from problem B. So I'll just copy this answer opposite letter B. The y equals 2. I will go now to problem C. The log of x to base 2 equals 3, and I will find the x. I will now write the equivalent exponential form of letter C, and that is 2 cubed equals x. Again, the log with base 2, I will copy that number 2 here as the base also of the exponent. The number 3 is the exponent itself, so that is 2 raised to 3. And this is equal to this number x, and I will copy it here. I will just simplify the 2 cubed, and this will give me 8. So 8 equals x. And this equation gives me the value that I want, that x equals 8. This is my answer. I will just copy this opposite letter C. So we are now complete with our answers for A, B, and C. Hi everyone. In this video, we're going to study more sample problems regarding logarithmic functions. Let's have example 1. Simplify each of the following using logarithmic properties. Letter A, log of 1 to base 16. Letter B, log of 125 to base 5. Letter C, e raised to log of 10 to base e. Let us write the properties that we're going to use to simplify the given problems here. For letter A, the log of 1 to base 16, we're going to use property number 1. It says here, for any base, and we're going to get the log of the number 1, the answer is always 0. So this is equal to 0. I will go to problem B. The log of 125 base 5. I'm going to use the property number 3. However, I need to do something to 125. I need to show that this 125 is equal to 5 cubed. So I have now log of 5 cubed to base 5. And as per our property number 3, we can simplify this into that exponent. So the answer here is 3. For problem C, the e raised to log of 10 to base e, we're going to use property number 4. And the answer here is the value which is 10. So the answer here is 10. So these are now the final answers. Let us go to example 2. Expand using the rules of logarithm. So this is log of a fraction where the numerator is 4x cubed z squared all over the denominator is y raised to 5 to base b. So this is taking logarithm of a quotient. So what we'll do is to get the log of the numerator minus the log of the denominator. So we have now log of 4x cubed z squared, that is the numerator, to base b, then minus the log of the denominator y raised to 5 to base b. In our first log here, there is a product, and to simplify that, we need to get the sum of the log of each of the factors. So let us expand this now. So we have log of 4, the first factor, to base b, plus the log of the second factor, x cubed, to base b, then plus the log of the third factor, the z squared, to the base b, then the minus log of the denominator, the y raised to 5 to the base b. We simply copied this last part here. So we have now 4 logarithms here. We can observe that there are exponents in each of the variables for the log here, here, and here. And we can still simplify that by making this exponent to be a factor of the log. So this is equal to the log of 4 to base b remains the same. Now for this log of x cubed, the exponent 3 we will put down here. So we have 3 log of x to the base b. Then plus the power 2 comes down as a factor. So we have 2 log of z to the base b. Then minus the exponent 5 comes down as a factor. So we have 5 log of y to base b. So this is now our final answer. Let us have example 3. Write the expression in terms of a single logarithm. So we have 2 log of x to base a plus 5 log of y to base a minus log of z to base a. We can observe here that the first two logarithms have constant in front of them. Here is number 2 and the other is number 5. We can simplify this by putting this constant as a power of the x. So let us write the problem again into log of x squared. Number 2 becomes the exponent of x to the base a, then plus the log of y raised to 5. Now the constant 5 becomes the power of y. And this is again to base a, then minus the log of z to base a. Then let us combine the first two logs. Because of this positive sign, we can put them as a product. So we have now the log of the product x squared y raised to 5 to the base a. And this log of z to base a, we just simply copy here. And to simplify further, this negative sign here denotes division, so we will put the two logs as a quotient. So we have the log of the fraction. First is the x squared y raised to 5 as numerator divided by the z, which becomes the denominator, and this is to base a. This is now our final answer. Let us have example 4. Solve for x. So we have here log of x to base b plus the log of the binomial x plus 1 to base b equals the log of 20 to base b. So this positive sign denotes product for the x and the x plus 1. So we will combine them. So we have now the log of the product x times x plus 1 to the base b equals, the right side is still the same, the log of 20 to base b. We have property number 5 that says the log of capital M to base b is equal to the log of n to base b if and only if m equals n. It means to say, since both the left side and the right side is a logarithm to base b, we can remove the logarithm directly to both sides. So you see here, the x times the x plus 1 comes down equals the 20. And from here, we will solve for x. We will distribute this x to each term of the binomial. So x times x is x squared. X times 1 is positive x. Now, for this 20, we're going to transpose on the left side of the equal sign, and the positive 20 becomes negative 20. And this is equal to 0. From here, let us solve by factoring. And the factors of x squared plus x minus 20 are x plus 5 times x minus 4. And this is equal to 0. And then for each factor, we will equate into 0. Let's start with the x plus 5. This is equal to 0. And the x minus 4 is also equal to 0. Then let us simplify both equations. X plus 5 equals 0. We will transpose the positive 5 to the right side. So we have x equals negative 5. And the other factor, the x minus 4, we will transpose the negative 4 to the right side, we have now x equals positive 4. And these are the values of x for the given problem. Let us have example 5. Solve for x. We have e raised to 1 minus 3x equals 9.62. From property number 5, it says the log of capital M to base b equals the log of capital N to base b if and only if m equals n. In this equation, we are going to apply logarithm to both sides of the equation. But since this is a variable e, we are going to apply a log with base e. So we have log of e raised to 1 minus 3x to base e equals log of 9.62 to base e. We did put e as the base for the log because we want to use property number 3 that says the log of b raised to x to base b can be simplified into x, and this x is simply the exponent of the b. It means to say we can simplify the left hand side. We can simply put the 1 minus 3x down here, and this is now equal to the log of 9.62 to base e. I hope you still remember about the natural logarithm that the log of x to base e is equal to the ln x. It means to say the log of e, we can change this by the ln symbol. So we have now the 1 minus 3x equals the ln of 9.62. Using our calculator, we can get the value of the ln 9.62, and this is equal to 2.26384. So let us now solve for x. This positive 1 we will transpose on the right side. Of course, the sign must be changed. So we have now the negative 3x equals 2.26384 minus 1. See here, the positive becomes negative 1. And to simplify further, we will get the difference of the two numbers here. So we have negative 3x equals 1.26384. And to make the coefficient of x equal to 1, we're going to divide the equation by the coefficient of x, which is negative 3. And if we do that, the negative 3 here will cancel out. So we have x equals the 1.26384 divided by the negative 3. And we can now simplify this into negative 0.42128. And this is the value of x that we are looking for. This is our final answer. I hope you learned something from this video. See you again next time.